Chapter 29 Physics Theory Video 4 Binding Energy and Stability. Now what we are going to do is we are going to figure out why some nuclei are more stable than the others. So now we spoke about some nuclei being unstable. So why is that? Because if everything is bound off, if all the electrons, if all the protons and neutrons are bound together by the strong nuclear forces, why are some of them unstable? So this is something that we need to figure out. So when the nucleus, if the nucleus is formed from separate nucleons, then the energy is going to be released. So then to pull them apart, we must add energy. So that means work must be done against the strong nuclear force that these nucleons are held together. So if there is more energy, that has been if more energy has been released, then the nucleus is going to be stable. That is, if we have to provide more and more energy to separate them, it is more stable. So the minimum amount of energy that is required to completely pull a nucleus apart to separate all the neutrons and protons individually separate, then we call that amount of energy, the minimum energy that is needed for that, is known as the minimum energy of the nucleus. So this is not the energy that is stored in the nucleus. It is the energy that we have to put, or that we have to give, or that we have to use, or the work done to pull apart the nucleus. For example, in the C612 carbon nucleus that we discussed earlier, the binding energy we calculated from the mass difference between C12 nucleus and the separate protons or the neutrons. So we need to consider binding energy per nucleon to get an idea as to how stable something is, and to compare the stability of the nuclides. So this is the way to determine the binding energy per nucleon for a nuclide. What we do is we have to determine the mass defect for the nucleus. You know how to calculate that. We discussed that earlier. Then using Einstein's equation, mass energy equation, we determine the binding energy of the nucleus by multiplying the mass defect by c square. Mass defect is multiplied by c square. Then divide the binding energy of the nucleus by the number of nucleons to calculate the binding energy per nucleon. Right? So that is something that we need to figure out. So this figure 29 point show the variation of binding energy per nucleon with nucleon number A for nuclei. So the red dot here, represents the plot for the iron 56 nuclide, that is Fe56 26 nuclide, from the worked example 4. The greater the value of the binding energy per nucleon, more tightly are the nucleons bound together in the nucleus. And also what we need to remember, that not all the nuclides are the same. Some are more tightly bound, some are less tightly bound. Right. So as you can see here, lithium and hydrogen, their binding energy. In hydrogen, the binding energy is quite at the bottom here. It is somewhere around 1. we will be see that we will be able to see that general trend is for light nuclei to have low binding energies per nucleon. Hydrogen is lowest; it has low value. However, helium has a higher binding energy than now. Helium should be here. Some hydrogen, helium, lithium. So we would suggest that helium to be somewhere here, but it is not. Helium is here. So that means there is a significant impact of something else that is there. So the high binding energy, it has a high binding energy, so that proves that it is very stable. Carbon C612 or 168, they are highly stable, and also they can be thought of 3 and 4 alpha particles bound together. Alpha is you need to remember, alpha is 4 2. So this multiplied by 2 will give you oxygen, multiplied by 4 will give you oxygen. 2 into 4 is 8, 4 into 4 is 16, so that is oxygen. Then this into 3 is, alpha into 3 is carbon 612. So we can think of them as, compare them as 3 and 4 alpha particles bound together. Then when alpha particles are bound together, that is, if it is a multiple of the alpha particle, they will have a higher binding energy. Usually, when nucleon number is greater than 20, binding energy per nucleon doesn't vary that much. For the greatest value of binding energy is for iron 5626. So that means it would require the most energy per nucleon to dismantle the nucleus of this atom. So it is the most stable isotope in nature. I hope that makes sense. So what we need to, most prominently, what we need to understand is how to do the questions, how to calculate the energies. So now here they have given, you have to follow those 4 steps that was given at the top. So remember these 3 steps you will have to follow. Determine the mass defect for the nucleus, then use Einstein's equation and find the binding energy by multiplying the mass defect by c squared, and then divide by the number of nucleons to get the per nucleon value. Now let's see. Nucleon 5626 iron, mass of the neutron is given, mass of proton is given, then mass of Fe nucleus is also given separately. Now we have to find out the mass defect. So the number of neutrons is 30, 56 minus 26. Then the mass defect is going to be 8.680. You add the sum of the protons and neutrons masses and then subtract the iron nucleus. Then we get a positive value 8.680, 10 to the power minus 28. So the binding energy is that, and then to find the binding energy you multiply that by the square of the speed of light. Then we get 7.812 into 10 to the power minus 11 joules. Then we divide it by 56 because there are 56 nucleons to find out the binding energy per nucleon. 14 into 10 to the power minus 13 joules. Then if you look at the chart here, you will be able to see that it agrees with the value that is given here. Write down binding energy and stability. Not all nuclei are equally stable, the more energy involved in making or breaking the nuclei, more stable the nucleus is going to be. Leave a line, put a star and write down. The minimum energy needed to completely pull a nucleus apart into separate nucleons is known as the binding energy of the nucleus. Binding energy per nucleon is calculated as follows. Number one, determine the mass defect for the nucleus. Number two, using Einstein's mass energy equation, calculate the binding energy of the nucleus by multiplying the mass defect by c squared. Number three, divide the binding energy of the nucleus by the number of nucleons to get the binding energy per nucleon. I hope that made sense. And if you understood the worked example 4, I want you to do question number 9 and 10. After doing those questions, let's go to binding energy fission and fusion. So we can figure out using the now we know what that fission, fusion, radioactive decay, which of these are going to happen using the binding energy. Now we know that fission is the process in which massive nucleus split to form two smaller fragments. Not just alpha and beta radiation, there are two fragments. Now if you take the isotope of uranium 235, it can split spontaneously, but that doesn't happen very often. But in a process called induced fission, uranium 235 can be made to split by absorbing a slow moving neutron. So in this process, what happens is one neutron gets absorbed by U235 and U236 is produced. That turns into two products. So what happens is U235 captures this neutron and becomes a highly unstable 236 uranium. Within a few microseconds, the fission of 235 will begin and will produce barium 142 and krypton 92, and also a very fast moving neutron. So a neutron is released. So you know actually two fast moving neutrons are produced. And the energy that is produced is released as kinetic energy because the total mass of the system is going to decrease and that energy is going to be converted into kinetic energy. So that is actually the result of, it is explained by Einstein's mass energy equation. Now in another way of looking at it is Uh, as shown in this 29.6 chart, have a look at it. Now, two fragments have greater binding energy per nucleon than the original uranium nucleus. So, as a result, uranium nucleus splits in that way, energy will be released. The total binding energy of 142 barium and 92 krypton is greater than the binding energy of 235 U. So that means the difference of the energies that is released. The neutron, it doesn't have binding energy because it is a single, it is a lone nucleon. So, so what happens is fission and fusion both will increase the binding energy per nucleon of the particles involved. So that is actually the idea here. Both fission and fusion will increase the binding energy. Fusion is going to be a situation. We know that our energy comes from the sun as a result of the fusion that takes place on the sun. So two very light nuclei will join together to form a heavier nucleus. So in the sun, this is what happens. Hydrogen nuclei fuse to form helium. So when again in the as we saw in the earlier chart, the final binding energy of the nucleus is going to be greater than the total binding energy of the fusing nuclei once again. So the difference in the energy, difference is the energy released in the fusion reaction. The high binding energy of now helium will have high binding energy. So as a result, they would very rarely they would go for fusion. So in our star, what happens is two hydrogens. We say that two hydrogens join together. However, what happens is deuterium joins together to form joins together with a proton, which is actually the hydrogen ion rather. It produces the helium nucleus. The binding energy is of deuterium is 2.2 mega electron volts, and the binding energy of helium 3 nucleus is going to be 7.7 mega electron volts. So energy released in the fusion reaction is going to be the difference 5.5 mega electron volts. That is the difference between the energies. So that is something that you need to understand. I hope that makes sense. It is a bit of a tricky part. If you did not understand, let me know, then I will explain it further. I want you to write down a note. Write down binding energy and stability. We did write a note on this. Binding energy, fission and fusion, write down. In determining Which nuclear process, fission, fusion, or radioactive decay, is likely to occur? We can use binding energy graphs. Fission, under that, right? This is the process in which a massive nucleus splits to form two smaller nuclei. Example, uranium 235, it's written like this. Would absorb a slow moving neutron to produce barium and krypton and two high energy neutrons. High energy means fast moving neutrons. Energy is released in the form of kinetic energy because the mass of the system reduces. The two fragments produced have greater binding energy per nucleon. Remember, we are not talking about binding energy. It is really easy to confuse because if you think that it is the energy contained in the nucleus, you are going to get everything wrong. Binding energy is the total amount of energy that we need to pull it apart. That is because that energy has been released. So that means it has actually, the energy content of it is lesser. I hope that makes sense. The two barium and krypton products would have more binding energy than uranium 235 because energy has been released. So the difference between the binding energies of uranium 235 and barium and krypton would be the energy released. Then write down fusion. In fusion, two smaller or lighter nuclei join together to form a heavier nucleus. In our Sun, hydrogen nuclei fuse to form helium nuclei. There are many different reactions, fusion reactions taking place on the Sun. This is one of them. Deuterium nucleus joins together with a proton to make a helium-3 nucleus. And then write down this equation. So try to do question number 11 and 12. When they ask you how likely it is to occur, what is more likely to occur, you will be able to you should be able to understand that using the details that they have given or the energy comparisons that they have given. Try to do it. If you have any questions, please raise them.